Class 11th Chemistry, Chapter 1 Some Basic Concepts of Chemistry. Chemistry is the science of molecules and transformations. It is the science not so much of 100 elements but of infinite variety of molecules that may be built from them. Roald Hoffmann. Science can be viewed as a continuing human effort to systemize knowledge for describing and understanding nature. You have learnt in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane juice, on keeping for prolonged time and rusting of iron are some of examples of changes which we come across many times. For sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure, and reactions of material substances is called chemistry. Development of chemistry. Chemistry as we understand it today is not a very old discipline. Chemistry was not studied for its own sake, rather it came up as a result of search of two interesting things: philosopher's stone Paras, which would convert all baser metals, example iron and copper, into gold; elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in form of alchemy and electrochemistry during 1300 to 1600 CE. Modern chemistry took shape in 18th century Europe, after a few centuries of alchemical traditions which were introduced in Europe by Arabs. Other cultures, especially the Chinese and Indian, had their own alchemical traditions. These include much knowledge of chemical processes and techniques. In ancient India, chemistry was called Rasayan Shastra, Ras Tantra, Ras Kriya, and Ras Vidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavations at Mohenjo-daro in Sindh and Harappa in Punjab proved the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction of work. It shows the mass production of pottery, which can be regarded as earliest chemical process in which material were mixed, molded and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been found in the construction work. It contains lime sand and traces of calcium carbonate. Harappans made faience, a sort of glass which was used in ornaments. They melted and forged a variety of objects from metals, such as lead, silver, gold, and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Musky in South India in 1000 to 900 BCE, and Hastinapur and Takshila in North India in 1000 to 200 BCE. Glass and glazes were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back in the beginning of Chalcolithic culture in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rig Veda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BCE. The golden gloss of black polish ware of northern India could not be replicated and is a still chemical mystery. These wares indicate the mastery with which kiln temperature could control. Kautilya's Arthashastra described the production of salt from sea. A vast number of statements and material described in ancient Vedic literature can be shown to agree with modern scientific findings. Copper utensils, iron, gold, silver ornaments, and terracotta discs and painted grey pottery have been found in many archaeological sites in northern India. Sushrut Samhita explains the importance of alkalis. Charak Samhita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc, sulfates of copper, zinc, and iron, and the carbonates of lead and iron. Ras Upanishad describe the preparation of gunpowder mixture. Tamil texts also describe the preparation of fireworks using sulfur, charcoal, saltpetre, that is potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a reputed chemist and alchemist and with a metallurgist. His work Ras Ratnakar deals with the formulation of mercury compounds. He has also discussed methods for extraction of metals like gold, silver, tin and copper. A book Rasavanam appeared around 800 CE. It discusses the use of various furnaces, ovens, and crucibles for different purposes. It described method by which a metal could be identified by flame color. Chakrapani discovered mercury sulfide. Credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soaps. Indians began making soaps in 18th century CE. Oil of iranda and seed of mahua plant and calcium carbonate were used for making soaps. The paintings found on the wall of Ajanta and Ellora, which look fresh even after ages, testify to a high level of science achieved in ancient India. Varamihir's Brihat Samhita is a sort of encyclopedia which was composed of 6th century CE. It informs about the preparation of glutinous material to be applied on walls and roofs of houses and temples. It was prepared entirely from extract of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such materials scientifically and access them for use. A number of classical texts, like Atharved, in 1000 BCE, mention some dye stuff. The material used were turmeric, madder, sunflower, opiment, cochineal, and lac. Some other substances having tinting properties were kamplika, patanga, and jatuka. Varamihir's Brihat Samhita gives references to perfumes and cosmetics. Recipes for hair dyeing were made from plants like indigo and minerals like iron powder, black iron or steel and acidic extracts of sour rice gruel. Gandha Yukli describes recipes for making scents, mouth perfumes, bath powders, incense and talcum powder. Paper was known in India in 17th century as account of Chinese traveler Wan Singh describes. Excavations at Takshila indicate that ink was used in India for 4th century. Color of ink were made from chalk, red lead and minimum. It seems the process of fermentation was well known to Indians. Vedas and Kautilya's Arthashastra mention about many types of liquors. Charak Samhita also mentioned ingredients such as bark of plants, stems, flowers, leaves, woods, cereals, fruits and sugar cane for making aswas. Concept that matter is ultimately made of indivisible building blocks appeared in India a few centuries BCE as a part of philosophical speculations. Acharya Kand, born in 600 BCE, originally known by name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small indivisible particles which he named Parmanu, comparable to atoms. He authored the text Vaiseshika Sutra. According to him, all substances are aggregated form of smaller units called atoms, Parmanu, which are eternal, indestructible, spherical, suprasensible, and in motion in the original state. He explained that this individual entity cannot be sensed through any human organ. Khan added that there are varieties of atoms that are as different as different classes of substances. He said these Parmanu could form pairs or triplets among other combination and unseen forces cause interaction between them. He conceptualized that this theory around 2500 years before John Dalton, 766 to 1844. Charak Samhita is the oldest Ayurvedic epic of India. It describes the treatment of diseases. The concept of reduction of particle size of metal is clearly discussed in Charak Samhita. Extreme reduction of particle size is termed as nanotechnology. Charak Samhita described the use of bhasma of metals in treatment of ailments. Nowadays, it has been proved that bhasmas have nanoparticles of metals. After decline of alchemy, electrochemistry reached a steady state, but it too declined due to the introduction and practice of Western medicinal system in 20th century. During this period of stagnation, pharmaceutical industry based on Ayurvedic continued to exist, but too declined gradually. It took about 100 to 150 years for Indians to learn and adopt new techniques. During this time, foreign products poured in. As a result, indigenous traditional techniques gradually declined. Modern science appeared in Indian scene in the later part of 19th century. By mid-19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that chemistry deals with the composition, structure, properties and interaction of matter and is of much use to human beings in daily life. These aspects can be best described and understood in terms of basic constituents of matter that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can we see, weigh and perceive these entities, atoms and molecules? Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and number of these particles? We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical values with the suitable units. Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas which are weather patterns, functioning of brain, operation of computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human needs for food and healthcare products and other material aimed at improving the quality of life. This is exemplified by large-scale production of variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides method for the isolation of life-saving drugs from natural sources and make possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug AZT, azithromycin, is used for helping AIDS patients. Chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new materials having specific magnetic and electrical optical properties. This has led to production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymers, metals, etc. These industries contribute in a big way to the economy of nation and generate employment. In recent years, chemistry has helped in dealing with some of the processing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmental hazardous refrigerants like CFC, chlorofluorocarbon, responsible for ozone depletion in stratosphere, have been successfully synthesized. However, many big environmental problems continue to matter of grave concern to the chemist. One such problem is the management of greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical processes, use of enzyme for large-scale production of chemicals and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristic of states of matter which you learnt in your previous classes. States of matter. You are aware that matter can exist in three physical states with solid, liquid and gas. The constituent particles of matter in these three states can be represented as shown in figure 1.1. Particles are held very close to each other in solids in an orderly fashion and there is no much freedom of movement. In liquids, the particles are close to each other but can move around. However, in gases, particles are far apart as compared to those present in solid or liquid state, and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. Solids have definite volume and definite shape. Liquids have definite volume but no definite shape. They take shape of the container in which they are placed. Figure 1.1, Arrangement of particles in solid, liquid and gas. Gases have neither definite shape, volume or definite. They completely occupy the space in container in which they are placed. There are three states of matter interconvertible by changing condition of temperature and pressure. Solid on heating becomes liquid, liquid on heating becomes gas. Gas on cooling becomes liquid, liquid on cooling becomes solid. On heating, solid usually changes into a liquid and liquid on further increasing changes to gas. In reverse process, gas on cooling liquefies to liquid and liquid on further cooling freezes to solid. Classification of matter. In class 9 chapter 2, you have learned that at the macroscopic level or bulk level, matter can be classified as a mixture of pure substances. These can further subdivided as shown in figure 1.2. When all constituent particles of a substance are same in chemical nature, it is said to be pure substance. A mixture contains many types of particles. Mixture contains particles of two or more substances which can be present in it in any ratio. Hence their composition is variable. Pure substances forming mixture are called its component. Many substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are mixtures. Mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of mixture are uniformly distributed throughout the bulk of the mixture and its composition is uniform throughout. Sugar solution and air are the example of homogeneous mixture. In contrast to this, in a heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixture of salt and sugar, grains and pulses along with some dirt are a heterogeneous mixture. You can think of many more examples of mixture which you come across in daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple hand picking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixtures. Constituent particles of pure substance have fixed composition. Copper, silver, gold, water and glucose are some examples of pure substances. Glucose contains carbon, hydrogen and oxygen in a fixed ratio and its particles are of same composition. Hence, like all pure substances, glucose has a fixed composition. Also, its constituents carbon, hydrogen and oxygen cannot be separated by simpler physical methods. Pure substances can further classified into elements and compounds. Particles of element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen are some example of elements. Their all atoms are of one type. However, the atom of different elements are different in nature. Some elements such as sodium or copper contain atom as their constituent particles, whereas in some others the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen and oxygen gases consist of molecules in which two atoms combine to give their respective molecules. This is illustrated in figure 1.3. Figure 1.3, representation of atoms and molecules. When two or more atoms of different elements combine together in a fixed ratio, molecule of compound is obtained. Moreover, the constituent of compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Example of some compounds are water, ammonia, carbon dioxide, sugar, etc. Molecule of water and carbon dioxide are represented in figure 1.4. Note that water molecule comprises of two hydrogen atom and one oxygen atom. Similarly, molecule of carbon dioxide contain two oxygen atom combined with one carbon atom. Thus, atom of different elements are present in compound in a fixed and definite ratio, and this ratio is characteristic of particular compound. Also, properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compounds formed by their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. Properties of matter and their measurement. Physical and chemical properties. Every substance has unique characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, and chemical properties like composition, combustibility, reactivity with acids and bases. Physical properties can be measured or observed without changing the identity of composition of the substance. The measurement or observation of chemical properties require a chemical change to occur. Measurement of physical property does not require occurrence of chemical change. Examples of chemical properties are characteristic of reaction of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. Measurement of physical properties. Quantitative measurement of physical properties is required for scientific investigation. Many properties of matter such as length, area, volume, etc. are quantitative in nature. Any of quantitative observation or measurement is represented by number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and m denotes meter, unit in which length is measured. Earlier two different systems of measurement, the English and metric system, were used in different parts of world. This metric system, which originated in France in late 18th century, was more convenient as was based on decimal system. Late need of common standard system was felt by scientific community. Such was established in 1960 and discussed in detail below. International System of Units (SI). International System of Units, in French, Les Systèmes International des Unités, abbreviation as SI, was established as 11th General Conference on Weights and Measures. CGPM from Conference Generale des Poids et Measures. CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as Metric Convention, which was signed in Paris in 1875. SI system has 7 base units and they are listed in table 1.1. These units pertain to 7 fundamental scientific quantities. Other physical quantities such as speed, volume, density, etc. can be derived from these quantities. Table 1.1 Base physical quantities and their units. Length L, SI unit meter. Mass small m, SI unit kilogram. Time small t, SI unit second. Electric current I, SI unit ampere. Thermodynamic temperature capital T, SI unit Kelvin. Amount of substance N, SI unit mole. Luminous intensity IV, SI unit candela. Definition of SI units given in table 1.2. SI system allows the use of prefixes to indicate multiple or submultiple of a unit. These prefixes are listed in table 1.3. Let us now quickly go through some of quantities which you will be often using in this book. Table 1.2 Definition of SI base units. Unit of length meter. Meter symbol m in SI unit of length. It is defined by taking fixed numerical value of speed of light in vacuum c to be 299792458 when expressed in unit meter per second, whereas the second is defined in terms of cesium frequency del VCS. Unit of mass kilogram. Kilogram symbol kg is the SI unit of mass. It is defined by taking fixed numerical value of Planck's constant to be 6.62607015 into 10 to power minus 34 when expressed in unit joule second, which is equal to kg meter square per second, where the meter and second are defined in terms of C and del VCS. Unit of time second. Second symbol S is SI unit of time. It is defined by taking fixed numerical value of cesium frequency del VCS and the perturbed ground state hyperfine transition frequency of cesium 133 atom to be 9192631770 when expressed in unit hertz, which is equal to second inverse. Unit of electric current ampere. Ampere symbol A is the SI unit of electric current. It is defined by taking fixed numerical value of elementary charge E to be 1.602176634 into 10 to power minus 19 when expressed in unit of C, which is equal to AS, where the second is defined in terms of del VCS. Unit of thermodynamic temperature Kelvin. Kelvin symbol K is the SI unit of thermodynamic temperature. It is defined by taking fixed numerical value of Boltzmann constant K to be 1.38069 into 10 to power minus 23 when expressed in unit of joule kilo inverse, joule Kelvin inverse, which is equal to kg meter square second minus 2 Kelvin minus 1, where the kilogram, meter and second are defined in terms of HC and del VCS. Unit of amount of substance mole. The mole symbol is the SI unit of substance. 1 mole contains exactly 6.022140076 into 10 to power 23 elementary entities. This number is the fixed numerical value of Avogadro constant Na. When expressed in the unit mole inverse, it is called Avogadro number. Amount of substance, symbol N, of system is a measure of number of specified elementary entities. An elementary entity may be an atom, molecule, and ion and electron, and any other particle or specified group of particles. Unit of luminous intensity, candela. Candela, symbol CD, is the SI unit of luminous intensity in a given direction. It is defined by taking fixed numerical value of luminous efficiency of monochromatic radiation of frequency 540 into 10 to the power 12 Hz KCD to be 683 when expressed in unit LM inverse, which is equal to CD SR W inverse or CD SR kg inverse meter power minus 2 second cube, where kilogram meter second are defined in terms of HC and del VCS. Prefixes used in SI system: 10 to the power minus 24 yocto, 10 raised to the power minus 21 zepto, 10 raised to the power minus 18 atto, 10 raised to the power minus 15 femto, 10 raised to the power minus 12 pico, 10 raised to the power minus 9 nano, 10 raised to the power minus 6 micro, 10 raised to the power minus 3 milli, 10 raised to the power minus 2 centi, 10 raised to the power minus 1 deci, 10 deca, 10 square hecto, 10 cube kilo, 10 raised to the power 6 mega, 10 raised to the power 9 giga, 10 raised to the power 12 tera, 10 raised to the power 15 peta, 10 raised to the power 18 exa, 10 raised to the power 21 zeta, and 10 raised to the power 24 iota. Mass and substance. Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by given gravity of object. The mass of substance is constant, whereas its weight may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. SI unit of mass is given in table 1.1 is kilogram. However, its fraction named as gram, 1 kg is equal to 1000 gram, is used in laboratory due to smaller amount of chemical used in chemical reaction. Volume. Volume is the amount of space occupied by substance. It has the unit of length cube. So, in SI unit system, volume has unit of m cube. But again, in chemistry laboratories, smaller volumes are used. Hence, volume is often denoted in centimeter cube or decameter cube units. A common unit liter, which is not an SI unit, is used for measurement of volume of liquids. 1 liter is equal to 1000 ml. 1000 centimeter cube is equal to 1 decameter cube. Figure 1.6 help to visualize these relations. Figure 1.6. In laboratory, the volume of liquid or solution can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of solution. These measuring devices are shown in figure 1.7. Figure 1.7. Some volume measuring devices: burette, pipette, graduated cylinder, volumetric flask. Density. The two properties mass and volume discussed above are related as follows. Density is equal to mass by volume. Density of a substance is its amount of mass per unit volume. So SI unit of density can be obtained as follows. SI unit of density is equal to SI unit of mass, SI unit of volume is equal to kg by meter cube. This unit is quite large and a chemist often express density in gram centimeter minus 3, where mass is expressed in gram and volume expressed in centimeter cube. Density of substance tell about how closely its particles are packed. If density is more, it means particles are more closely packed. Temperature. There are three common scales to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. Here K is the SI unit. The thermometer based on these scale are shown in figure 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degree to 100 degree, where these two temperatures are freezing point and boiling point of water respectively. The Fahrenheit scale is represented between 32 degree to 212 degree. Temperature on two scale are related to each other by the following relationship. Degree Fahrenheit is equal to 9 by 5 of degree Celsius plus 32. Kelvin scale is related to Celsius scale as Kelvin is equal to degree Celsius plus 273.15. It is interesting to note temperature below 0 degrees Celsius are possible in Celsius scale, but in Kelvin scale negative temperature are not possible. Figure 1.8, temperature using different temperature scales. Uncertainty in measurement. Many times the study of chemistry has to deal with experimental data as well as theoretical calculation. There are meaningful ways to handle the number conveniently and present data realistically with certainty to extent possible. These ideas are discussed below in detail. Scientific notation. As chemistry is the study of atoms and molecules which have extremely low masses and present in extremely large numbers, and a chemist has to deal with numbers and large as 602 to 00 up to 15 zeros. For molecule of 2 gram of hydrogen gas or as small as 0.000 up to 15,0166 gram mass of hydrogen atom. Similarly, other constants such as Planck constant, speed of light, charge on particle involve number of above magnitude. It may look funny for a moment to write or count number involving so many zero, but it offers a real challenge to do simple mathematical operation of addition, subtraction, multiplication, division of such number. You can write any two number of above type and try one of the operation you like to accept as challenge, and then you will really appreciate difficulty in handling such number. This problem is solved by scientific notation of such number, that is exponential notation, in which any number can be represented in form n into 10 to power n, where n is any exponent having positive or negative value and n is a number which varies between 1.00 and 9.999. Thus, we can write 232.508 as 2.32508 into 10 square in scientific notation. Note that while writing it, the decimal had to move to the left by 2 places, and same is exponent of 10 in the scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 to power minus 4. Here the decimal has to move 4 places to right and minus 4 exponent in scientific notation. While performing mathematical operation on number expressed in scientific notation, following points are to be kept in mind. Multiplication and division. These two operations follow the same rules which are there for exponential number. 5.6 into 10 raised to power 5 into 6.9 into 10 raised to power 8 gives 5.6 into 6.9 in the bracket into 10 to power 5 plus 8 is equal to 5.6 into 6.9 into 10 to power 13, which gives 3.864 into 10 to power 14. 9.8 into 10 to power minus 2 into 2.5 into 10 to power minus 6 gives 9.8 into 2.5 in bracket into 10 to power minus 2 minus 6, which gives 2.450 into 10 to power minus 7. 2.7 into 10 to power minus 3 divided by 5.5 into 10 to power 4 gives 2.7 divided by 5.5 into 10 to power minus 3 minus 4, which is equal to 4.909 into 10 to power minus 8. Addition and subtraction. For these two operations, first the number are written in such a way that the same exponent after the coefficient digits are added or subtracted in case may be. Thus, for adding 6.65 into 10 to power 4 and 8.95 into 10 to power 3, exponent is made same for the numbers. Thus, we get 6.65 into 10 to power 4 plus 0.895 into 10 to power 4. Then these numbers can be added as follows. Similarly, 6.65 plus 0.895 into 10 to power 4 gives 7.545 into 10 to power 4. Similarly, subtraction of two numbers can be done as shown below. 2.54 into 10 to power minus 2 minus 4.8 into 10 to power minus 3 is equal to 2.5 into 10 to power minus 2 minus 0.48 into 10 to power minus 2. 2.5 minus 0.48 into 10 to power minus 2 is equal to 2.02 into 10 to power minus 2. Significant figures. Every experiment measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and skill of person making the measurement. Because, for example, mass of object is obtained using a platform balance and comes to be 9.4 gram. On measuring mass of object on analytical balance, mass comes to be 9.4213 gram. The mass obtained is higher than the mass obtained by using platform balance. Therefore, digit 4 placed after decimal is measurement by platform balance is uncertain. The uncertainty in experimental or calculated value is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus one with estimated or uncertain. Uncertainty is indicated by writing certain digits and last uncertain digit. Thus, if we write a result of 11.2 ml, we say 11 is certain and 2 is uncertain. Uncertainty would be plus minus 1 and last digit. Unless otherwise stated, the uncertainty of plus minus 1 and last digit is always understood. There are certain rules to determine the number of significant figures. These are stated below. All the non-zero digits are significant. For example, in 285 cm there are 3 significant figures and in 0.25 ml there are 2 significant figures. Zeros preceding to the first non-zero digit are not significant. Such zero indicates to the position of decimal point. Thus 0.03 has one significant figure and 0.0052 has two significant figures. Zeros between two non-zero digits are significant, thus 2.005 has four significant figures. Zeros at the end of right of number are significant, provided they are on the right side of decimal point. For example, 0.200 gram has three significant figures, but if otherwise the terminal zero are not significant if there is no decimal point. For example, 100 has only one significant figure, but 100 has three significant figures. 100.0 has four significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 into 10 to power 2 for one significant figure, 1.0 into 10 to power 2 for two significant figure, and 1.00 into 10 to power 2 for three significant figures. Counting the number of objects, for example, 2 ball or 20 eggs have infinite significant figures as these are exact number and can be represented by writing infinite number of 0 after placing of decimal. That is 2 is equal to 2.000000 or 20 is equal to 20.000000. In number written in scientific notation, all digits are significant. Example, 4.01 into 10 square has 3 significant figures and 8.256 into 10 to power minus 3 has 4 significant figures. However, one would always like the result to be precise and accurate. Precision and accuracy are often referred to while we talk about measurement. Precision refers to closeness of various measurement of same quantity. However, accuracy is the agreement of particular value to the true value of result. For example, if a true value of result is 2 gram, student A takes two measurement and reports the result as 1.95 gram and 1.93 gram. These values are precise as they are close to each other but are not accurate. Another student B repeats the experiment and obtains 1.94 gram and 2.05 gram as the result. These observations are neither precise nor accurate. When third student C repeats these measurements and reports 2.01 gram and 1.99 gram as result, these values are both precise and accurate. This can be more clearly understood from the table given in below. Student A first 1.95 and 1.93, average 1.940. Student B 1.94 and 2.05, average 1.995. Student C 2.01 and 1.99, average 2.000. Addition and subtraction of significant figures. Result cannot have more digit to the right of decimal point than either of original number. 12.11, 18.0, 1.02 is equal to 31.122. Here 18.0 has only one digit after the decimal point and result should be reported only up to one digit after decimal point, which is 31.1. Multiplication and division of significant figures. In these operations, the result must be reported with no more significant figure in the measurement with few significant figure. 2.125 is equal to 3.125. Since 2.5 has two significant figure, result should not have more than two significant figure, thus it is 3.1. While limiting the result of the required number of significant figure as done in above mathematical operation, one has to keep in mind the following points for rounding of the numbers. If rightmost digit is to be removed is more than 5, the preceding number is increased by 1. For example, 1.386, if we have to remove 6, we have to round off it to 1.39. If rightmost digit is to remove less than 5, the preceding number is not changed. For example, 4.334, if 4 is to be removed, then result is rounded off to 4.33. If rightmost digit is to removed is 5, then the preceding number is not changed if it is even number but is increased by 1 if it is odd number. For example, 6.35 is to rounded by removing 5. We have to increase 3 to 4, giving 6.4 as the result. However, if 6.25 is to be rounded off, it is rounded off to 6.2. Dimensional analysis. Often while calculating, there is need to convert units from one system to other. Method used to accomplish this is called factor label method or unit factor method or dimensional analysis. This is illustrated below. Example, piece of metal is 3 inch long. What is length in centimeter? We know 1 inch is equal to 2.54 centimeter. Hence, 1 inch by 2.54 is equal to 2.54 by 1 is equal to 1. Thus, this factor also equal to 1. Both are called unit factor. If some number is multiplied by unit factors, it will not affect otherwise. Say for 3 in above, 3 inch is equal to 3 into the factor is equal to 3.2.54 is equal to 7.62 centimeter. Now unit factor by multiplication is to be done. That unit factor which gives the desired unit, that is numerator, should have that part which is required in the desired result. It should be noted in above example that units can be handled just like other numerical part. It can be cancelled, divided, multiplied, squared, etc. Let us study one more example. A jug contains 2 liter milk. Calculate a volume of milk in meter cube. As 1 liter is equal to 1000 centimeter cube, 1 meter is equal to 100 centimeter. So 1 by 100 is equal to 100 by 1. To get meter cube from the above unit factor, the first unit factor is taken as is cube. Factor cube is equal to 1. 2 liter is equal to 2 into 1000 centimeter cube. Above factor multiplied by unit factor 2 into 1000 centimeter cube into 1 meter cube by 10 to power 6 centimeter cube is equal to 2 meter cube by 10 cube is equal to 2 into 10 to power minus 3 meter cube. Example, how many seconds are in 2 days? We know 1 day is equal to 24 hours. So 1 day by 24 hours is equal to 1. So 1 hour is equal to 60 minutes. Hence, 1 hour by 60 minutes is equal to 60 minutes by 1 hour. For converting 2 days to second, 2 days is equal to dash second. Unit factor can be multiplied in series in one step only as follows, which give the result 172800 second. Law of chemical combination. The combination of elements to form compound is governed by 5 basic laws. Antony Leviosa. Law of conservation of mass. This law was put by Antony Leviosa in 1789. He performed careful experimental studies for combustion reaction and reached to the conclusion that in all physical and chemical changes there is no net change in mass during the process. Hence he reached the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. This law formed on the basis of several later developments in chemistry. In fact, this was the result of exact measurement of masses and reactants and products. Carefully planned experiments performed by Leviosa. Law of definite proportion. Joseph Proust. This law was given by French chemist Joseph Proust. He stated that a given compound always contains exactly the same proportion of element by weight. Proust worked with 2 samples of cupric carbonate, one of which was a natural origin and other was synthetic. He found that the composition of element present in it was same for both samples as shown below. Thus he concluded, irrespective of source, given compound always contains same element combined together in same proportion by mass. The validity of this law has been confirmed by various experiments. It is sometimes referred as law of definite composition. Law of multiple proportion. This law was proposed by Dalton in 1803. According to this law, if 2 elements can combine to form more than one compound, the masses of one element that combine with fixed mass of other element are in fixed ratio of small whole number. For example, hydrogen combine with oxygen to form 2 compounds, namely water and hydrogen peroxide. Hydrogen 2 gram plus oxygen 16 gram gives water 18 gram. Hydrogen 2 gram plus oxygen 32 gram gives hydrogen peroxide 34 gram. Here, masses of oxygen which combine with fixed ratio of hydrogen bear a simple ratio, that is 1:2 or 16:32. Gay-Lussac's law of gaseous volume. This law was given by Gay-Lussac in 1808. He observed that when gases combine are produced in a chemical reaction, they do so in simple ratio by volume provided all gases are at same temperature and pressure. Thus, 100 ml of hydrogen gives 50 ml of oxygen to give 100 ml of water vapor. 100 ml hydrogen plus 50 ml oxygen gives 100 ml of water. Thus, volume of hydrogen and oxygen which combine bear a simple ratio 2:1. Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportion by volume. The law of definite proportion stated earlier was with respect to mass. Gay-Lussac law was explained properly by the work of Avogadro in 1811. Avogadro's law. In 1811, Avogadro proposed that equal volume of all gases at same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atom and molecule, which is quite understandable in present time. If we consider again the reaction of hydrogen and oxygen to produce water, we see that 2 volume of hydrogen combine with 1 volume of oxygen to give 2 volume of water without leaving an unreacted oxygen. Note that in figure 1.9, page 116, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecule to be polyatomic. If hydrogen and oxygen were considered as diatomic as recognized now, then the above results are easily understandable. However, Dalton and others believed that time atom of same kind cannot combine and molecules of oxygen and hydrogen containing 2 atoms did not exist. Avogadro's proposal were published in French journal De Physique. In spite of being correct, it did not gain much support. After about 50 years, in 1860, the first international conference on chemistry was held in Karlsruhe, Germany, to resolve various ideas. At the meeting, Stanislaw Cannizzaro presented a sketch of course of chemical philosophy which emphasized on the importance of Avogadro's work. Dalton atomic theory. Although the origin of idea that matter is composed of small indivisible particles called atomio, meaning indivisible, dates back to the time of Democritus, a Greek philosopher, it again started emerging as a result of several experimental studies which led to laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. Matter consists of indivisible atoms. All atoms of a given element have identical properties including identical mass. Atoms of different elements differ in mass. Compounds are formed when atoms of different elements combine in fixed ratio. Chemical reaction involve reorganization of elements. They are neither created nor destroyed in a chemical reaction. Dalton theory could not explain the laws of chemical combination, however, it could not explain the law of gaseous volume. It could not provide the reason for combining of atoms, which was unanswered later by other scientists. Atomic and molecular mass. After having some idea about the terms and atoms of molecules, it is appropriate. Atomic mass or mass of atom is actually very small because atoms are extremely small. Today we have sophisticated techniques, example mass spectrometry, for determining the atomic mass fairly accurately, but in 19th century scientists could determine the mass of one atom relative to another by experimental means. As has been mentioned earlier, hydrogen being the slightest atom was arbitrarily assigned as mass of 1 and other elements were assigned mass relative to it. However, present system of atomic masses is based on carbon-12 as the standard has been agreed upon in 1961. Here carbon-12 is one of the isotopes of carbon and can be represented as 12 carbon. In this system, 12 carbon is assigned as a mass of exactly 12 atomic mass unit and masses of all other atoms are given relative to this standard. One atomic mass unit is defined as measure exactly equal to 1/12 of mass of one carbon-12 at 1 AMU is equal to 1.66056 into 10 to power minus 24 gram. Mass of an atom of hydrogen is equal to 1.6736 into 10 to power minus 24 gram. Thus, in terms of AMU, the mass of hydrogen atom is equal to 1.67 into 10 to power minus 24 gram by 1.66056 into 10 to power minus 24 gram is equal to 1.0078 AMU is equal to 1.008 AMU. Similarly, mass of oxygen 16 would be 15.995 AMU. At present, AMU has been replaced by EU. which is known as unified mass. When we use atomic mass of elements in calculation, we actually use average atomic mass of element, which are explained below. Average atomic mass, many naturally occurring elements such as more than one isotope, we take account the existence of these isotopes and relative abundance. Average atomic mass of element can be computed. For example, carbon has following three isotopes with relative abundance and masses as shown against them. Isotopes of carbon. From above data, average atomic mass comes out to be 12.0011 U. Similarly, average atomic mass of other elements can be calculated. In the periodic table of elements, the atomic mass mentioned for different elements actually represent their average atomic mass. It may be noted that sodium chloride 1Na plus ion is surrounded by 6Cl negative ion and vice versa. Formula such as NaCl is used to calculate formula mass instead of molecular mass in solid state. Sodium chloride does not exist as a single entity. Thus, formula mass of sodium chloride is atomic mass of sodium is equal to atomic mass of chlorine is equal to 23 plus 35.5 is equal to 58.5. Mole concept and molar masses. Atoms and molecules are extremely small in size and their number are in even in a amount of substance is really very large. To handle such large numbers, a unit of convenient magnitudes is required. Just we denote 1 dozen for 12 atoms, score for 20, gross for 144. We use the idea of 1 mole to count entities at microscopic level. In SI unit, mole was introduced as 7th base unit quantity for the amount of substance. The mole symbol is the SI unit of amount of substance. 1 mole contains exactly 6.022140076 into 10 to the power 23 elementary entities. This number is the fixed numerical value of Avogadro constant Na when expressed in the unit mole inverse and is called the Avogadro number. Amount of substance, symbol N of system, is a measure of number of specified elementary entities. An elementary entity may be an atom, molecule, or an ion, electron, any other particle or specified group of particles. It may be emphasized that mole of a substance always contains the same number of entities, no matter what the substance may be. In order to determine this number precisely, mass of carbon-12 atom was determined by a mass spectrometer and found to be equal to 1.9 into 10 to the power minus 23 gram. Knowing 1 mole of carbon equal to 12 gram, the number of atoms is equal to 12 gram per mole, which is equal to 6.02 into 10 to the power 23 atoms. Having defined the mole, it is easier to know the mass of 1 mole of substance or constituent entities. Mass of 1 mole of substance in gram is called its molar mass. Molar mass in gram numerically equal to atomic molecular formula mass. Molar mass of water is equal to 18.02 gram per mole. Molar mass of sodium chloride is equal to 58.5 gram per mole. Percentage composition. As we were dealing with the number of entities present in a given sample, but many times information regarding percentage of particular element present in compound is required. Suppose an unknown or new compound is given to you. The first question you would ask is what is the formula or what are its constituents and in what ratio they are present in the given compound. For known compounds also, such information provides check whether the given sample contains the same percentage of element as present in pure sample. In other words, one can check the purity of given substance by analyzing the data. Let us now understand it by taking example of water. Since water contains hydrogen and oxygen, percentage composition are mass percent of element is equal to mass of element in compound into 100 by molar mass of compound. Mass of water is equal to 18.02 gram. Mass percent of hydrogen is 11.18. Mass percent of oxygen is equal to 88.79. Empirical formula or molecular formula. Empirical formula represent the simple whole number ratio of various atoms present in a compound, whereas molecular formula show the exact number of different types of atom present in a molecule of compound. If the mass percent of various element present in compound is known, its empirical formula can be determined. Molecular formula can further be obtained if molar mass is known. The following example illustrate this. Stoichiometry and stoichiometric calculation. Word stoichiometry is derived from two Greek words stoichion and metron. Stoichiometry thus deals with the calculation of masses of reactants and products involved in chemical reaction. Before understanding how to calculate the amount of reactant required or product produced in a chemical reaction, let us study what information is available from the balanced chemical reaction. Let us consider combustion of methane. Balanced chemical equation for this: CH4 gas plus 2O2 gas gives CO2 gas plus 2H2O gas. Here methane and dioxygen are called reactant and carbon dioxide and water are called product. Not all reactant are product and gases in above reaction, and this has indicated by letter G in bracket next to its formula. Similarly, in case of solids and liquids, respective L and S. Coefficient of O2 and H2 are called stoichiometric coefficients. Similarly, coefficient of CH4 and CO2 in one case. They represent the number of molecules taking part in the reaction and form in the reaction. Thus, according to the above chemical reaction, 1 mole of CH4 reacts with 2 mole of O2 to give 1 mole of CO2 and 2 mole of H2O. 1 molecule of CH4 reacts with 2 molecule of O2 to give 1 mole of CO2 and 2 molecule of H2O. 22.7 liter of CH4 react with 45.4 liter of oxygen to give 22.7 liter of carbon dioxide and 45.4 liter of H2O. From these relations, the given data can be interconverted as mass into moles and number of molecules. Mass by volume is equal to density. Limiting reagent. Many times reactions are carried out with the amount of reaction that are different than the amount required by balanced chemical reaction. In such situation, one reactant is more amount and the other amount required by balanced chemical reaction. Reactant which is present in least amount get consumed after some time, and after that further reaction does not take place whatever be the amount of other reactant. Hence the reactant which get consumed first limits the amount of product formed is called limiting reagent. In performing stoichiometric calculation, this aspect is also to kept in mind. Reaction in solution. Majority of reaction in laboratory are carried out in solution. Therefore, it is important to understand how amount of substance expressed in solution. Concentration of solution or the amount of substance present in given volume can be expressed in any of the following ways: mass percent, weight percent, mole fraction, molarity, molality. Let us now study each of them. Mass percent obtained by using following relation: mass percent is equal to mass of solute by mass of solution into 100. Mole fraction, it is the ratio of number of moles of particular component of the total number of moles of solution. If a substance A dissolves in substance B and the number of moles Na and Nb respectively, then the mole fraction of A and B are: mole fraction of A is equal to number of moles of A by number of moles of solution, Na by Na plus Nb. Mole fraction of B is equal to number of moles of B by number of moles of solution is equal to Nb by Na. Molarity, it is the most widely used denoted by M, capital M, defined as number of moles of solute in 1 liter of solution. Thus, molarity is equal to number of moles of solute by volume of solution in liter. Suppose we have 1 molar solution of substance of NaOH, we say to prepare 0.2 molar solution from it. If 1 molar NaOH means 1 mole of NaOH present in 1 liter of solution, for 0.2 m solution, we require 0.2 moles of NaOH dissolved in 1 liter. Hence, for making 0.2 solution, for 1 m solution, we have to take that volume of 1 molar NaOH which contains 0.2 mole of NaOH and dilute this solution with water to 1 liter. Now, how much volume of concentrated NaOH solution to taken which contains 0.2 mole of NaOH can be calculated as follows. 1000 ml by 1 mole into 0.2 mole solution gives 200 ml solution. Thus, 200 ml of 1 m are taken in enough water to add to dilute it to make 1 liter. In fact, such calculation, general formula M1V1 is equal to M2V2 where M and V are molarity and volume can be used. In this case, M1 is equal to 0.2 molar, V1 is equal to ml, M2 is equal to 1.0 molar. V2 is to be calculated. Substituting values in formula, V2 is equal to 200 liter. Note, number of moles of solute NaOH was 0.2 into 100 ml and remained the same. 0.2 even after dilution, as we have changed the amount of solvent and have not done anything with respect to NaOH. But keep in mind the concentration. Molality. It is defined as number of moles of solute present in 1 kg of solvent. It is denoted by M. Thus, molality is equal to number of moles of solute by mass of solvent in kg.